Good evening and welcome. So, gravitational waves, the discovery that won the Nobel Prize. I am Neeti Sonth, the webmaster of MTAP. I'm honored to represent Tinka Ross, who is in our audience tonight, the eminent founder of the Mt Tam Astronomy Program. Before we start, I request everyone to hold their questions until the end of the presentation. You can unmute yourselves to ask a question or paste the question in the chat, and hopefully I do a good job of reading it for you. All right. It is my pleasure to introduce tonight's speaker, Dr. Lynn Cominsky. Lynn Cominsky is an award-winning professor in the Physics and Astronomy Department at Sonoma State University. Professor Cominsky grew up in the snows of Buffalo, New York, and attended college at Brandeis University, where she studied chemistry and physics. After graduating from college, she worked at the Harvard-Smithsonian Center for Astrophysics, analyzing data from the first X-ray astronomy satellite, Uhuru. She went to graduate school in physics at MIT, and after getting a PhD there in 1981, she moved to California. She has been on the faculty at Sonoma State University for over 35 years and chaired the Department of Physics and Astronomy for 15 years before stepping down. Professor Cominsky is the founder and director of SSU's Education and Public Outreach Group, now renamed EdEon STEM Learning, which develops educational materials for NASA, NSF, and the US Department of Education. In 1993, Professor Cominsky was named SSU's Outstanding Professor and the California Professor of the Year by the Council for the Advancement and Support of Education. Professor Cominsky has earned many fellowships and honors throughout her career. Recent awards include the 2016 Education Prize from the American Astronomical Society, the 2016 Wang Family Excellence Award from the California State University, and the 2017 Frank J. Malina Education Medal from the International Astronautical Federation. In 2019, she was selected as one of the first 200 Legacy Fellows named by the American Astronomical Society. Cominsky's most recent project is NASA's Neurodiversity Network, N3, creating inclusive informal learning opportunities across the spectrum. N3's goal is to provide a pathway to NASA participation and STEM employment for neurodiverse learners with a focus on the autism spectrum. Please welcome Professor Lynn Cominsky.
Okay, thank you for that very nice introduction. Since it's such a small group, I don't think you need to wait to hold your questions till the end. So if there's something that is confusing, definitely put it in the chat right away so that I've at least managed to keep you with me as we go through this talk. Okay, and of course, I wish I was on Mt Tam right now instead of sitting here in front of my computer like I've been doing for the past 2 years. But I'm still happy to tell you about the exciting work that's been done in the last few years with LIGO and Virgo, and most recently CAGRA, although they haven't seen anything yet. More about that later. Okay, so what is all the excitement about? I was lucky enough to be at the press conference in Washington, D.C. on February 11th, 2016, where we made the big announcement.
Ladies and gentlemen, we have detected gravitational waves. We did it.
Okay, so why is everybody so excited? That's Dave Wrightsey. He's the LIGO laboratory director. To his left is Dr. Franz Cordova, who was the head of the National Science Foundation at the time. All the way over here is Dr. Gabriela Gonzalez, who was the spokesperson for LIGO. And these two gentlemen are two of the eventual 3 Nobel Prize winners. This is Ray Weiss from MIT and Kip Thorne from Caltech. So that was who was in the panel, and I was one of the many hundreds of people that were in the audience. So what's all the excitement about, and what are gravitational waves anyway? So we like to explain them by saying that gravitational waves are ripples in the fabric of space-time. But what does that mean? Okay, so first look at the little cartoon on the bottom left, and you're a point mass in the middle here, this little black guy in the middle. And all of these masses are being deformed as a gravitational wave passes through space-time. First, it squeezes in one direction while stretching in the other direction, and then half a cycle later, it does the opposite. So now imagine lots of these little masses going through space, and you can see that it makes something that looks like it's rippling. Right, there we go. Right, so that looks like ripples through space-time as the wave passes through these different planes of little test masses. So Einstein predicted that gravitational waves would exist when he put out his theory of general relativity in 1915. That was not something that had been thought about before. Einstein thought about it. If you were somebody who was living on the Earth and wasn't thinking like Einstein thought, you might have thought about gravity from Newton's point of view. And here's a cartoon done by my wonderful artist at Sonoma State, Aurora Simonet, sort of illustrating the apocryphal story of Newton sitting under an apple tree and looking up the moon and realizing that the same force that made the apple fall to the ground was keeping the moon in orbit around the Earth. And in Newton's point of view, you had to have two objects to have gravity be a force between them. And this force would be transmitted instantaneously and is given by this equation here with Newton's gravitational constant, the two masses, and divided by the square of the distance between them, as illustrated in this picture. So what's wrong with that picture? Well, here's Einstein's view of gravity, and it's not quite as simple to understand, but when you see a diagram like this that has all of these grid lines with what's appearing to be a warp in the grid, this is how we usually portray the warping of space-time due to the presence of mass. The problem is that it's really warped in 4 dimensions, 3 dimensions of space and 1 dimension of time. And all we can do to make a drawing of it is try to make something that looks 2-dimensional down here to illustrate the warp. But really, the space-time is warped in every possible dimension around the spherical mass. It's just impossible to draw that or to really visualize it, especially because you have to warp time as well. And there's no way to draw that. But at least from this kind of cartoon, you can see that a small mass object like the Earth would make a much smaller dent in the fabric of space-time than a big object like the sun, a very massive object like the sun. And so this is called an embedding diagram, and this is the way that we usually represent the warping of space-time, just because if you had lines going everywhere in all dimensions, you wouldn't be able to really see the objects. So if you compare the two theories of Newton versus Einstein, from Newton's point of view, space was flat and time was constant. But with Einstein, space and time are intertwined. In fact, we are moving through space and through space-time at the speed of light. Even though you may feel like you're sitting still right now, you are aging 1 second per second. So you're sitting still and time is passing. But if you start to move through space-time and you go faster and faster, time slows down. So space and time are intertwined in Einstein's way of looking at things. They're not separate objects or separate measurements. So in Newton's point of view, you needed to have 2 masses to make this force between them. But from Einstein's point of view, because gravity is due to that curvature, that warping of space-time, all you need is 1 mass, and that's plenty. From Newton's point of view, the force of gravity is instantaneous, whereas in Einstein's theories, the gravitational waves, or the fastest you can transmit information about a change in gravitational strength, would be at the speed of light, which is usually called the letter C. For Newton, light travels in a straight line, And for Einstein, light follows the shortest path through curved spacetime, which is usually called a geodesic. So it's really very different when you look at, sort of the basic ways of thinking about gravity from the two different theories. Okay, so, well, what about black holes? Well, black holes are infamous for not letting light escape from within a certain radius, which is usually called the event horizon. And the event horizon is the place in space, it's a spherical place all the way around the object, where the escape velocity from that object would have to be equal to the speed of light. And since you can't go faster than the speed of light, if you go inside the event horizon, you can't go faster than the speed of light, so you can't get out. Right at the event horizon, if you are going at the speed of light, you can get out. And right outside the event horizon, if you're going, a little bit less than the speed of light, you can get out. But black holes are something that had been theorized for a long time. And as you'll see with the discovery of gravitational waves, we now have direct evidence for black holes that obey Einstein's equations in the theory of general relativity. It's also important to note that when you're making a stellar-sized black hole from a star that has exploded in a supernova, if the core of that star does not have enough mass to collapse all the way down to a black hole, it'll stop and make a neutron star.
Hi, my name is Jeff. I was wondering if I can ask a question while we're trying to figure this out. Although you may need help to coordinate figuring it out, so let me know if timing is wrong. But when you, on the previous slide, you talked about single mass. Was that the word? So can you define or describe single mass, please?
Okay, so in this picture, either one of these would be sufficient, right? Because either one of these masses by themselves, the mass of the Earth or the mass of the sun, is enough to cause a warp in space-time. And this curvature of this grid-like, fake grid-like structure that we use to depict the curvature is actually gravity. Right? So in Einstein's theory, the fact that any particular mass, so just look at either one of them, doesn't have to be both of them. Either one of them is enough to make a warping of space-time, and so either one of them has gravity all by itself without having to have the other one there to be acted on. Did that help?
Yes. And so in theory, and again, let me know if there's like some coordination needed where this is not question time anymore, but I'm
not sure that I can help them, so I'll
okay.
keep talking to you.
So in theory, what this is saying is that, because when I think about Einstein, I think about relativity, and so what I'm thinking about that, and I'm not physics trained, is things working in relation to one another. And so what it sounds like you're saying with single mass is
there's a special theory of relativity, which has to do with frames of reference when things are moving at a constant velocity. And then the general theory has to do with what's happening when things are accelerating and not moving at a constant velocity. And so one way to accelerate is to move in a circle, and another way to accelerate is to change speed. Right? So you can change either the speed or the direction of movement, and either one of those counts as acceleration. So when you have two things orbiting each other, you can see clearly how that is an accelerating situation. But really, a single mass all by itself, just sitting here, warps space-time, and any other object that would come near it would then feel that curvature of space-time and respond to the gravity by having to move through this curved space-time.
That's really helpful. Thank you.
Okay, well, we'll just keep going and we'll see if we get anybody else that shows up at some point. All right, so we were up to black holes, making neutron stars if a star explodes and doesn't have enough mass to make a black hole from its core. Okay, so why am I telling you about black holes? Because I'm trying to explain what our knowledge was of stellar mass black holes before the LIGO discovery of gravitational waves. So the very first black hole was called Cygnus X1, and that is because it was the first X-ray source discovered in the constellation Cygnus the Swan. And when they got an accurate position for the X-ray source, they were able to identify the supergiant companion star shown in the upper right. And then they were able to monitor the supergiant companion star and see it wobble around the orbit of something they couldn't see, which is the black hole. And when you fit this curve of the wobble, the radial velocities, as the lines are Doppler shifting, blue shifting as they're coming towards you, red shifting as the object's moving away from you, you can analyze this Doppler curve and determine the mass of the unseen object. And the mass of the black hole is most likely 16 plus or minus 5 times the mass of our sun. And that's typical of the other stellar mass black holes that have been found to date. And this black hole, Cygnus X1, was identified and measured in the early 1970s. Another thing that happened in the 1970s was that indirect evidence for gravitational waves was discovered by Joe Taylor and Russell Hulse's graduate student. And they did this by studying neutron stars instead of black holes. And so there is a binary neutron star called PSR for pulsar 1913 plus 16, where two neutron stars are orbiting around each other. And because they can measure both of them, they can figure out what the masses of both of them are, and they're 1.4 times the mass of our sun. And one of the neutron stars is a pulsar, which means it's acting like an atomic clock. It's spinning around every 59 milliseconds and making these pulses, which you can track very, very accurately. And so as you do this over a period of now, longer than this, but here's 30 years worth anyway. Or maybe 20, 30 years worth. And of course, now it's closer to 2025. You see the red dots are the data and the blue curve is Einstein's theory. And it couldn't be more perfect, right? And the error bars on these little red dots are little tiny blue things sticking out if you can see them. So what's happening is energy is leaving the system of these two neutron stars that are orbiting around each other. And as the energy leaves the system by being emitted in gravitational waves, the stars get closer together. And this is plotting the decay of the orbit. So it's showing you how the stars are approaching each other. And eventually, after millions more years, the neutron stars will collide. And the gravitational waves will stop being emitted. So there's been a lot of theoretical work, of course. And so what if you could see two black holes orbit around each other and then merge to make a bigger black hole? What if you could see that with electromagnetic radiation? That would be, in this case, visible light. It would look something like this. So the two black holes are the two big black things in the middle, and their gravity is making the light from the stars behind them come in front of them. And when you see these little whiskers develop, there's one right there. That's actually the other black hole's light being bent all the way around the black hole with the whisker. There's actually warping space-time that much. Oh, there they go. They just merged. They made a big black hole. It sort of relaxes a little bit, and then that's the end of it. Now, this particular computer simulation is an actual simulation using all of the full equations of general relativity. It's not an artist's conception. With exact solutions using supercomputers. It took thousands of hours of supercomputers to make that movie. This one, on the other hand, is an artist's conception. And this is what the gravitational waves would look like. So here's two black holes. Here's our space-time grid so that you can see the warping. It starts out, you can see sort of big waves, but the waves will get to be closer together and also higher in amplitude as the two black holes approach each other. So there they go. And you can see the waves moving out. And they're going to go faster and faster as they get closer to each other. See, now the waves got taller, they merged, and then that's the end of the event. Okay, so that's what it's supposed to look like if we see it in gravitational waves. So this is a little technical, but both gravitational waves and electromagnetic waves, otherwise known as light waves, travel at the speed of light, and they're both transverse waves, which means their amplitude is going this way and the waves are going at a perpendicular direction. Electromagnetic waves are usually caused by accelerating charged particles, but gravitational waves are produced by the acceleration of massive bodies. And so it's a quadruple effect because mass doesn't have a positive and a negative. Charged particles have positives and negatives, and so you can get an electromagnetic wave from accelerating a charged particle. It's called the dipole radiation. But since there's only one kind of mass and gravity is always attractive, you need to have accelerating masses around each other to make the gravitational waves. And also when we are detecting them, we're only looking at the amplitude, we're not really looking at the energy. And so that gives us an observational advantage because it falls off more slowly as a function of distance to the source. So that's a good thing. Okay, now for a little more background, a little bit about LIGO. So LIGO stands for Laser Interferometer Gravitational Wave Observatory. So we've talked about the gravitational waves. I haven't told you about the lasers or the interferometer part. So this is a little cartoon animation that basically shows how LIGO works, but not in much detail. So the laser beam sends out a signal. It goes through a beam splitter. Half of it goes in the Y direction, half of it goes in the X direction. That was the wave passing through. And now we'll just slow it down so you can see it better. So there's the wave. It went through the beam splitter. Half of the wave goes to on one axis, turns around, comes back again. The same thing happened on the other axis. Now they recombine back at the beam splitter. If they're exactly out of phase, you won't see any signal here at the detector because they're canceling each other. But as the gravitational wave goes through, it changes the length of the arms so that they can constructively interfere, and then you get to see a signal out of this end. So there, it just shows you, here's the detector, and you can see that it gives you this sort of pulsing signal as the waves interfere constructively and then destructively and then constructively again. So that's the interference part. But in order to make all of this work, it takes an incredible amount of very sophisticated hardware and 2 different observatories in the US so that you can check to see whether the signals are actually correct or if they're caused by something else. So the 2 LIGO observatories, one is in the big nuclear reservation up in Hanford, Washington. The other one is in Livingston, Louisiana, in the middle of a big forest. LIGO is so sensitive that when the people are logging in the forest and cutting down the trees make big waves that can easily be detected by LIGO, the one in Livingston. And so during the daytime, when the people are working in the forest, it's a very noisy background in Livingston compared to Hanford, which, as you can see, has nothing much around it. So it's sort of the answer to the question, if a tree falls in the forest and no one's there to hear it, can anybody hear it, right? And of course, LIGO can hear it. So you don't have to be there. But it does create a lot of background noise in what you're looking for. Now, Hanford, Washington is up here, and Livingston, Louisiana is down here. And also, this red thing shows the way that the X and Y axes, the 2 different legs of the interferometer, are pointing for Hanford, and it's the opposite of Livingston. Also, if the wave is coming from space and hitting both of them at the same time, that gives you information about the direction. If it comes from this direction, it could hit Livingston first and later hit Hanford. There would be a 10 millisecond delay if it went exactly across the US and sort of the plane of the globe, right? If it's coming this way at both of them, it'll hit them both at the same time. It gives you information about the circle on the sky of positions that could have created that time delay difference in the signals between the 2 observatories. So for a general wave, a gravitational wave in general, you would expect there to be a time difference between the two signals, as well as, since they're oriented opposite, the waves would be detected upside down from each other. And in fact, that's just what we saw. So let me just summarize all the background stuff that I've gone through, because I'm just going to show you the real data in the next set of slides. Gravitational waves were predicted by Einstein's general theory of relativity, which he put out in 1915, and it was published in 1916. Gravitational waves travel at the speed of light. The more massive the bodies are, the stronger the gravitational waves are. And when they collide, you get the strongest ones. We're going to be looking at the wave patterns to learn about the masses of the objects. This is directly comes out of Einstein's theories. We're going to look at the amplitude of the waves to figure out the distance to the objects. And we're going to look at the time delays between the two detectors to try to figure out where they're coming from in space. Okay, everybody with me so far? Any questions out there? Anybody? You're good so far? Okay. So here's what LIGO observed. This is the very first gravitational wave ever seen. This was on September 14th, 2015. Here's the Livingston data. Here's the Hanford data. They've already flipped it upside down, and they've already adjusted for the time delay. And you can see that they look very similar. So you start with smaller waves. As the waves grow in amplitude, they get sharp, higher frequencies. Same thing happens over here. This is the actual best fit model now drawn through both of those plots. So a little bit lighter color, you can see the best fit model right from Einstein's equations. So what are we actually looking at? Okay, so this is time on the x-axis, and this whole plot is only about 0.2 of a second long. On the y-axis, the amplitude is plotted in these interesting units called strain that have units of 10 to the minus 21. So what is strain? Strain is the change in the length of one of the arms of the interferometer divided by the whole length of the interferometer arm. The length of the interferometer arms for LIGO are 4 kilometers. The maximum strain that we see is about 10 to the minus 21. So that means that each arm is changing by only 4 times 10 to the minus 18 meters. That's 4,000 times smaller than a proton. That's incredible that you can measure something that accurately. It's like measuring the width of your hair with a ruler that is as long as the distance to the nearest star. It's pretty astonishing. There's no other thing on Earth that can make measurements that are this accurate of a distance. And what this curve shows here, this plot shows you the sensitivity curve of LIGO. All of these big spikes are places where it's not very sensitive because of instrumental effects. But if you just look at this curve underneath here. So at the time that we started in 2015 and 2016, the best strains that we could measure were about 10 to the minus 23. And what we were measuring for the waves was 2 orders of magnitude higher strain, 10 to the minus 21. So quite easily detectable. Also, the frequencies that we're measuring these over go from 20 hertz to about 2000 hertz. Okay, a hertz is a cycle per second, but the sweet spot for LIGO is between 100 and 1000 hertz. So when LIGO was designed, they tried to make this be the most sensitive region, because the only things we knew about that might make gravitational waves at the time were this binary pulsar system that was discovered by Taylor and Hulse, who won the Nobel Prize in 1974. So we did not know that there were binary black holes that would be heavier and slower, and that would be coming out at much slower frequencies. We thought they would be 1.4 solar mass neutron stars, and the frequency should be in this range based on that one binary pulsar that people had observed at the time. Okay, so what did we actually find? So this is the signal that I just showed you, and we name these things after the year. So 2015, the month, September, and the day, 14th. This first event that was so strong that it was 2 orders of magnitude above our sensitivity limit was caused by a 36 solar mass black hole merging with a 29 solar mass black hole, making a 62 solar mass black hole. And if you add up 36 and 29, it doesn't make 62, it makes 65. And so the other 3 solar masses of energy were emitted in the gravitational waves. This source was located at 410 million parsecs, which is about 1.2 billion light years, or a redshift of 0.09. The black hole that was formed afterwards, the big 62 solar mass guy, it was spinning at 2/3 of the maximum rate for a black hole of its size. That's what the spin parameter is. So this was pretty astonishing. All the black holes that we had known about from looking at X-ray data and measuring those Doppler curves like Cygnus X1, they were all in the range of 15 to 20 solar masses. And we couldn't really prove that they were black holes. We could just say there's something that has this mass. We don't see anything from it of visible light. We're only seeing X-rays from outside the event horizon. So it was indirect evidence for a black hole. This is direct evidence for not 1, but 2 black holes. They're way heavier, way more massive than anything we had seen before with X-ray astronomy. And the one they made was so much heavier that, you know, it just, everyone's minds were just blown. I mean, it was just astonishing. And because these waveforms fit so exactly to Einstein's theories that are describing what a black hole is, it is actually the first direct evidence for black holes, as well as measuring the masses, as well as finding a binary black hole, which nobody even knew could exist until this happened. So it was an incredibly exciting discovery from a lot of different angles. So what we like to do with these things, so that you can relate to them a little bit more as a human being, is a process called sonification, where we turn the waveform signal into a sound you can hear with your ears. And because it's getting louder and higher frequency, it goes ooh, and we call that kind of frequency pattern a chirp. And so because this one is so slowly moving, and it's also over in only 0.2 seconds, because that's how long it stayed in the LIGO bandpass, it doesn't sound very chirpy until I shift it up frequency-wise so you can hear it a little better. So this recording is going to play what it sounds like at the actual frequency, and then it's going to shift it up by 400 hertz so that our ears can actually hear it a little better, and it'll repeat. And this is called the spectrogram, and here's the waveform that you previously saw, but here's it getting brighter and higher frequency, right? That's the chirp behavior there. So I hope everybody could hear that. I just thought this was a funny cartoon that came out right after the discovery. So just a little humor. And here's a lovely drawing that my artist made that shows both of the signals overlaid, so you can see just how well they match each other. Of course, the one has been shifted by a little bit and flipped upside down. But this phase is the in spiral, where the 2 black holes are still going around each other, and it's just making regular waves. Now they're starting to merge, and the waves are getting bigger and higher frequency. And then finally, after the final merger, it's that sort of quivering jelly-like ring down that you saw in the simulation before. And if you'd like to have a copy of that particular thing, we made a poster out of it. I'm part of a group called Contemporary Physics Education Project, and so we made a poster that you can buy on Amazon or through our website that explains Newton, black holes, Einstein, emerging pulsars, and the big discovery, of course. If you have a classroom, I invite you to go buy one of those posters. Okay, so at the end of 2017, we had the following 5 events. This is the first one, where we had a 29 and a 36 merging to make a 62. This one was not as statistically significant, although later reanalysis, it became more significant and it got a GW name. These 2 black holes are more like the size of Cygnus X1. But of course, then when they merge, they make something that's twice the size of Cygnus X1. This one, little smaller ones, this is called the Boxing Day event because it was the day after Christmas, which is Boxing Day in the UK. Then that was it for observing run number 1. Then we turned LIGO off for all of 2016 so we could upgrade it and come back on with more sensitivity when 2017 started. And then we saw these 3 events in 2017. And now Virgo has joined in, and Virgo is starting to see some of these events as well. Virgo is an interferometer in Italy. But the most amazing thing we saw in 2017 was the thing that we had started off looking for originally, which is merging neutron stars. And so we had long believed that merging neutron stars would make a big blast of gamma rays when they merged, called the gamma ray burst. And people have been studying gamma ray bursts since the late 1960s and had seen 2 different kinds of gamma ray bursts, the shorter ones of which were supposed to be from neutron star mergers, but we could never really prove it until this event. So now you're going to see the LIGO signal, and then you're going to see what the Fermi gamma ray satellites saw. And you're going to hear them both as well. Oops. Let me try that again. I missed clicking on the right thing. There we go. So 2 seconds after the final chirp, the final merger of the neutron stars, we see the gamma ray burst come out. And that was very interesting because people didn't know that there would be a time delay between the burst and the actual merger. The merger happened when the chirp finished. But it takes gamma rays a long time to get out of all of the swirling matter and all of the debris and stuff before you can see them. And so that seems to make sense now that we've seen this one. But this event was so incredibly exciting that 1/3 of the astronomers in the entire world were looking at this thing with every single possible telescope that they could find. And the first people that saw it with a visible light telescope was the team based at UC Santa Cruz that used a telescope called the SWOPE telescope. And they saw this thing show up that 4 days later was fading away. But there were 70 different ground-based telescopes that were looking for this thing, as well as every telescope that anybody had up in space. Hubble looked at it, Chandra looked at it, various gamma ray telescopes looked at it. It was pretty amazing. The papers that came out about this had 3,000 authors on them. And I was 2 of them. There were so many authors, they couldn't even tell that people were on there more than once. But I was on the Fermi team and I was on the LIGO team, so I got listed twice. Anyway, definitely the most authors on a paper that I've ever been on. But it was just incredibly exciting. And then because a NASA satellite saw it, NASA decided to do a visualization. So this is just an artist's conception of what it might have looked like, complete with sound, which you will not hear in space. So ignore the sound, it's very dramatic, but that's the NASA way of visualizing things. Both jets are sending out gamma rays. Hitting the interstellar medium and glowing. So that's NASA's view of what they think is happening, but ignore the music. There's no music in space. So what did we see? Well, when we analyze the waveforms, we can find out the masses of the two objects. They weren't 1.4 like the binary pulsar originally discovered in the 70s. They were 1.2. And so the problem is that 1.2 plus 1.2 makes 2.4 at best. Most theories for black hole formation, stellar mass black hole formation, you need to have at least 3 solar masses in that core to make a black hole. So we don't really know what was formed. It could have been a black hole. It could have been a fatter neutron star. We're not really sure what they merged into. That's the subject of active research right now. But the major thing that we did learn, and that everybody agrees on, is that all of this ejected material from these neutron stars, which had all these neutrons in them and all these pieces of heavier atoms, ended up making neutrons capture onto the heavier atoms and making at least half the heavy elements that we see in the universe today, including gold and platinum and things like that, that are heavier than iron. Because inside a star, when the star is burning nuclear fuel and then goes supernova and then spews everything out, you only get as far as iron. If you want to get past iron and see the rest of the heavy elements in the periodic table, you've got to capture more neutrons into those iron cores and keep building it up until you get to the heavier elements. And it is this kind of process that can do that. And they saw direct evidence for that process happening in the visible light spectra. So that's where the estimate that at least half the heavy elements, including gold, come from our so-called golden binary. And this lovely illustration by my artist, Doris Simonette, made the cover of Nature and is the iconic image now that everybody uses to depict merging neutron stars. And these jets, of course, are supposed to be representing the things that make the gamma rays. And here's the 2 merging neutron stars. And here's all the swirling stuff around it that's making all the heavy elements. Now you can see that they're very different. The top 5 are the original black hole mergers. The bottom one is the neutron star. It's going to run through the actual data that we have. And remember, the top one was all over in 0.2 of a second. So as this one keeps going, the bottom one keeps going, we actually were able to detect it for almost 100 seconds. Whereas all of these black hole ones, we could only detect for a few tenths of a second to a couple seconds at most. And so they're really quite different waveforms and quite different lengths of time. But remember, I told you LIGO was designed for neutron stars, and so it stays in the bandpass for a lot longer. The black holes are moving much too slowly, and we're just not sensitive to those slower frequencies. So they only stay in the bandpass at the very end when they're merging, just for a very short period of time. Okay, now I think we're going to start to hear the chirp. There it goes. So 55 seconds long. These other guys were less than a second in general. Okay, so right after that, that was August of 2017. Right after that, in October of 2017, the Nobel Prize got announced. But it was really based on the original black hole detections from 2015, because they had already picked the Nobel Prize winners before we got the golden binary signal. And so here's Ray Weiss from MIT and Kip Thorne from Caltech. And the guy in the middle is Barry Barish, who is also from Caltech and who was one of the original project managers. And so they collected a whole lot of other prizes besides the Nobel Prize. They got at least 3 or 4 other prizes that were also each worth about $1 million to each one of them. It's quite an amazing thing. And I know at least Ray Weiss has turned around and given almost all of the money back in terms of scholarships and stuff for people at MIT. And that's only because I'm from MIT that I know that. I don't know what happened with the Caltech guys. And then in March of 2018, we had a collaboration meeting, the LIGO Virgo collaboration meeting at Sonoma State. And so there's me posing with the Nature cover of my artist poster and our little cat that we call Ogiel, which is LIGO backwards. And then we had a banquet dinner for all of us who couldn't go to Sweden to celebrate the Nobel Prize. And so this is 3 of my students and me hugging Kip Thorne. And Ray Weiss was there too. And we had a lovely time. So at the end of observing run 2, which was the end of 2018, this is what we had discovered. So all of the neutron stars that we were able to measure masses of electromagnetically are down here in yellow. Here's the one LIGO Virgo neutron star. So a 1.2 and a 1.2 making about a 2.4. These purple ones are the electromagnetic black holes like Cygnus X1. And all of these blue triples are the ones that were discovered with LIGO and Virgo. Okay, so, not bad. So we call that Observing Run 1 and Observing Run 2 catalog. Then we started the third, we shut down again, the detectors again. And then in 2019, we turned back on again for O3A, which lasted for 6 months, and then shut down for a month, fixed a few things. O3B lasted for another, supposed to be 6 months, but you can see what happened here, COVID. So instead of going for 6 months, everything had to shut down in March of 2020 as the world came to an end temporarily. And unfortunately for the Japanese folks that built the Kagra detectors, they finally got ready to join us in February 2020, right before everything had to shut down for COVID. So the bottom line summary for Observing Run 3 is that we did not find any more electromagnetic counterparts. People developed apps to let you know when there'd be an incoming gravitational wave so you could try to move your telescope. We saw 44 events in O3A and then another 35 events in O3B. So we went from just having a handful of events, maybe 20 total at the end of O2 to 90. I guess 11. Okay, we went from 11 to 90. Not bad. I think they finally were getting good at fixing the sensitivity of the detectors. So here's a result from O3A. It was on April 25th, 2019. It is a binary neutron star merger, but we didn't see a gamma ray burst, and so we couldn't do a very good job with the position because only the gamma ray telescopes give you a good position compared to LIGO. But it was the heaviest total for this merger. It got above the magic number of 3 solar masses, and so we do believe that a black hole is formed. One or both of the individual neutron stars are heavier than the 1.4, or it could have been a black hole and a neutron star. We're not sure. But here's Aurora's drawing of that one. So that we did see a second merger. We just couldn't tell you that much about it because we didn't have all those telescopes also able to see it. And the second result from O3A was very interesting because the two black holes that merged were so wildly different in mass. And so when you have this unequal mass thing merging, you get fancier looking waveforms and it predicts the shapes, and they were seen. Those higher harmonic shapes were seen as predicted by general relativity, which is very exciting. But also it breaks some of the computational when you can't tell the difference between two different things. And so doing this kind of fitting with the two different masses allows you to get a better distance, the tilt that you're observing the system to, and the spin of the heavier black hole. And also, is the system wobbling as it's orbiting each other? So that was very exciting because anytime you get an event that's really different, it gives you a chance to test more predictions of Einstein's theories. And amazingly enough, they're still working. It's always worked. Einstein's always been right. Here's a computer simulation of the unequal masses of the black holes merging. And this is another one of these simulations with using the full up general relativity equations. So it's not an artist's conception, it's an actual calculation with thousands of hours of supercomputer time. And they made really interesting, pretty waveforms from this, but it's also not at all running in real time, because if you look at the time down here, we're like minus 16 milliseconds away from the merger. So it's really going much faster than this. Now they're just blowing up the inner part so you can see it a little better. And now we're getting closer to the merger. I'm going to start to go a lot faster. Now you can see the beautiful wave pattern. I was just going to focus in on the merger. You notice they're also a little crooked. I have to stop it and switch to a different computer code to continue on with the merger. So, okay. No, we don't want to see it again. So in 2021, we announced the discovery of 2 possible mergers of a neutron star and a black hole. And one of the operators of LIGO, who then went off to become a graduate student, that's me, did this funny cartoon of Ray Weiss, making a list, checking it twice. What have we seen? Okay, we got a binary, we got black holes, we got neutron stars, we got an electromagnetic counterpart, and now we have 2 black hole neutron stars. Still to be discovered, an exploding supernova, an individual pulsar spinning around in an asymmetric way, and the stochastic gravitational wave background. So that was very exciting. And this is just a drawing, not a movie. But basically, you know, you've got this black hole and you've got this neutron star. And so there should be some matter left over. If it doesn't all go down the black hole, there is a chance to see electromagnetic counterparts from such events. And here's just a little comparison, how far away they were, what the masses were. So we've got, you know, something that's lightweight, like around less than 2 solar masses roughly. And then we've got a heavier, you know, 7 to 10 solar mass black hole kind of thing. And this is artist conception simulation of one of these events. So not a general relativity calculation, it's an artist conception. Okay, so this is basically where we are. We've just published the 3rd gravitational wave transient catalog. It's gone all the way through O3b. We've been shut down now since mid-2020 to continue to improve the sensitivity. We are looking at starting back up again in the very end of 2022. So hopefully December of this year. And when we start back up again, we should have LIGO and Virgo and Kagra. So 2 LIGO detectors, 1 Virgo detector, and Kagra in Japan. The more detectors we have, the better positions we can get without needing electromagnetic telescopes. But this is our summary. We've got 90 gravitational wave events so far. Only 1 was seen with electromagnetic radiation. The lightest object was 1.2 solar mass neutron star. The heaviest black hole that was made was about 107 times the mass of our sun. And we can see stuff all the way out to about 8 billion parsecs, which should be about 24 billion light years, 240 billion light years. So I'm looking forward to 04. It's going to be great. Here's the graphic of that catalog with the electromagnetic ones still in red and yellow, and all of the LIGO mergers in blue, but drawn sort of in a straight line so they'll fit on one plot, all 90 of them. Except for here's the ones where maybe it's 2 neutron stars making a black hole, we're not sure. A neutron star and a black hole making another black hole, right? So there's all the different kinds are represented on here. And this is the observatories that we are looking forward to having in the future. So here's the 2 LIGOs in the US. Here's Kagra in Japan. Here's Virgo in Italy. GEO 600 is an engineering interferometer in Germany. But we are building LIGO in India. Hanford used to have an extra set of detectors. It doesn't do us any good to have any more detectors in the Northern Hemisphere. We really wanted to go to Australia, because the further apart we are on the Earth, the better positions we can get in the sky when we have our overlapping circles. Australia didn't have the money. So the furthest south we could get was India, and India has the money, and they are building this now. And we're hoping for LIGO India to come online in 2024-ish or 5-ish. But the land has been acquired. They're starting to build the infrastructure. They've got the detectors over there. It is going, smoothly now. Very exciting. Lots and lots of people hard at work in India. Many, many different institutes in India working on this. Ayuka is one of them. But just like electromagnetic waves have a spectrum of different energies, gravitational waves do as well. And the ones we've been seeing are the shortest ones that have milliseconds. And that's what you can do if you have a 4-kilometer baseline. If you want to see longer waves, you need to have something like LISA, that would be laser interferometer space antennas out in space. Instead of a 4-kilometer baseline, you'd have something like a 5 million kilometer baseline. Or you could, so that's on the drawing board. People are working on that. Very tricky technology. You need to have these 3 satellites all know where they are to within very high levels of accuracy in the distance to be able to figure out the time delays and things like that. This is happening right now. This is called nanograv. So what you have is a bunch of radio telescopes on the Earth looking at a bunch of millisecond pulsars in the sky. And there are at least you need at least 35 well-studied millisecond pulsars. So they have very short periods. And then and they're all accurately known. Then when the gravitational wave comes through the sky, it'll affect the periods of each of those pulsars differently. And you can then pull that signal out by looking at how much each pulsar signal has shifted as the space between the pulsars has been stretched and squeezed as the wave passes. So that's funded by the National Science Foundation, as was LIGO, and people are looking right now, but no one's seen anything yet. And then if you want even longer periods for gravitational waves, you should be able to see an imprint of gravitational waves in the polarization of the cosmic microwave background. And there was an experiment called BICEP that claimed that it saw that before LIGO detected its waves, but it was wrong. It was really seeing dust, and so they had to retract that paper in case you'd heard of it. But we are now in the era of multi-messenger astronomy: electromagnetic waves, light waves, gravitational waves, cosmic rays, which are particles, neutrinos, which are ghostly particles. We can detect all these things from space, and each type of messenger tells us something new about our universe. And when we put together all the different kinds of information that we get from all of these different messengers, we call that the era of multi-messenger astronomy. And we are now in that era, which is very exciting. When I was a graduate student, we were just starting to do multi-wavelength electromagnetic astronomy. It was considered amazing back when I was a grad student 40 years ago that you could get X-rays and visible light both from the same thing, right? That was multi-wavelength astronomy. This is multi-messenger astronomy because we've gone beyond the electromagnetic spectrum to include all different kinds of waves and particles. So I will close with an in-spiral toast to the rise of multi-messenger and gravitational wave astronomy. This is invented by our LIGO colleagues in Scotland. And now I'm happy to take questions. And here are some resources for you to go look up some of the stuff that I've been talking about.
So much, Professor. Anyone has any questions? Okay, if not, I have a couple of questions. So I think you did show a strain plot, I think a couple of slides back. I was wondering if like the brightness or the intensity kind of increases, it's less, the amplitude is less, and then it increases and then it decreases again. Is that showing the black holes, like the binary black holes merging, and then, you know, like they merged?
Yeah, so it sort of has a low level of intensity while it's just orbiting, but as the two objects get closer and closer together, the intensity increases, so the strain goes up, and also they go faster and faster right before they merge, and so the frequency of the wave increases, so it gets louder and more highly pitched if you are, you know, thinking about it in terms of sonification or in terms of a chirp. And then once it's merged, It just jiggles a little bit and then it's over. So then it goes back down again.
Yeah, and so I think the time scale was, I think you mentioned it happens at a very short time, like, milliseconds.
Yeah, for the very first event that we saw, because they were such big, heavy black holes, we could not detect them with LIGO until they were going fast enough to get into our bandpass. And that meant that we only saw the last 0.2 of a second before the merger. Whereas with the neutron star binary, we had between 50 and 100 seconds worth of data where we could detect it, because it was right in the sweet spot of LIGO sensitivity. And of course, LIGO was designed for merging neutron stars because that's all we knew about before LIGO. No one had any idea or even had made any predictions about merging black holes, because we had no evidence for binary black holes anywhere in the universe. It's not something that can be observed electromagnetically.
Thanks. Yeah, that helps. And one of the question was, I think you did mention, I think the mass that of the combined or the merged black hole was lesser than the sum, because we have the gravitational waves being emitted. I was wondering, is gamma ray also being emitted, or that's specific to only neutron stars merging?
So conventional wisdom has been that you can see gamma rays when the neutron star merge, because there's all this material around to be lit up by the shock wave that will get accelerated to high enough energies to make gamma rays. But with the black holes, if you just have two black holes and they merge and make a bigger black hole, there's not all these swirling clouds of matter left over, because the black holes were not matter to start with. They were just pure gravity, basically. So now it's maybe possible that you could have black holes merge in an environment where there's a bunch of material around. And that has been suggested for some of the more recent events. It seems like you could have a big supermassive black hole in the center of a galaxy, a billion solar masses. Then that galaxy has lots of swirling matter around it. It's usually called an active galaxy. You could have two smaller black holes in the outskirts of the active galaxy, but they have matter around them. And then if they merge in that kind of environment, they could make an electromagnetic signal. And so there's some weak evidence that possibly that has happened, but we need more examples. We need to know more about it. It's a great theory. I love the theory. I just don't know if it's correct yet. We need more data, as always.
Okay. Yeah. Thanks for the explanation. That is an amazing presentation. One of the other questions was, there was a comparison you're showing about I think Einstein and Newton, their theories, and I think you mentioned time is constant for Newton. So yeah, is that does that mean he's saying time is not relative? Is that what you meant?
Well, from Newton's point of view, time is this fixed thing. It just marches forward and it's always at the same rate, right? But with general relativity, and this is like the twin paradox kind of classical thing, the twin that goes off and travels near the speed of light comes back and is younger than the twin that stayed at home. Okay. Right? Because time is passed more slowly for the moving twin. So the faster you go in space, the slower you move through time. It's just that we don't in general go fast enough to notice any change in the clock, right? You have to go really close to the speed of light, or at least some percentage of the speed of light that's non-negligible, to be able to see that time dilation effect.
Right. Okay. Thanks. Yeah, I think Jeff has a question.
Jeff, please. Like his hand is up. So.
Yeah. Thank you. This was, first of all, I hadn't really touched physics in a very long time, so this was incredibly interesting and super exciting. I just hadn't been around to hear about it. Okay. So thank you so much for all that. But also, I wanted to ask specifically around the supermassive black hole that's supposedly in the center of whatever the things.
Pretty much any galaxy that you could name. Yeah.
And so what are the expectations? Is the expectation that this is a merger of so many of these black holes and they've all merged and merged and merged?
That is
Or-
really an excellent question. So where did those really supermassive black holes come from? We understand where the stellar mass black holes came from, because you can imagine 100 mass, solar mass star at the beginning of the universe, and then it blows up and it leaves behind a big core that can make a black hole. That would be 20, 30 solar masses. But how do you get to be a billion solar masses? Our Milky Way galaxy has a 4 million solar mass black hole, and the active galaxies can have billion solar mass black holes in the center. Very good question. A related question, which came first, the galaxy or the black hole? So there was a big cloud of matter. Did the black hole collapse down in the middle and then the galaxy form around it? Or did the galaxy form and then the middle collapse and make the black hole? And people don't know that. Current evidence is that they actually grew up together, because there's a correlation between the size of the black hole and in the mass of the black hole that we've measured and the size of the galaxy, the mass of the galaxy. So it looks like they just sort of formed at the same time. But really, it seems to also be a primordial process. There's no way that we know of, even with colliding galaxies, that you could get them to be so big, starting out at 50 or something and get to a billion. You'd never have that many collisions to make something that would be a billion solar masses later.
Yeah,
So we don't know.
That's awesome. And I guess my mind just immediately goes to the sort of the eventualities. So like, we've heard about like the infinitely expanding universe and how it sort of like peter out of mass of mass and just become kind of boring.
Yeah, well, if the acceleration is, if the expansion is accelerating as it appears to be, then things will keep getting further and further apart, and there'll be fewer mergers later.
And that being said, there's also, it seems, these black holes which are sort of contributing some of their mass into gravitational waves, and so it seems like there's maybe like a bit of a dance there. Any comments on that?
Well, the gravitational waves, we can detect them, but they're not really moving things a whole lot. It's not like they come by and sweep something into something else. Yeah, that doesn't happen. So
it's too weak of a force, in other words, to sort of
gravity is actually just a super weak force compared to electromagnetic forces.
Mm-hmm.
About a factor of 10 to the 19 different, I think, if I remember correctly from my beginning physics problems.
Cool, thank you.
Anyway, if questions occur to you later and you would still like to know the answers, just feel free to send me email. I'm all over the internet. I answer email at any time of the day or night. Very strange times, as you will see if you ever write me. There's my email address. I've just put it in the chat. So feel free to reach out with any more questions. I'm always happy to talk to people about fun physics like this.
Thank you, Professor.
I want to express my appreciation to you for taking the time and giving us this presentation. It was really very illuminating, very clear and understandable, which is not always the case when we hear some very technical talks. And I really appreciate your presentation very much. Thank you so much for joining us.
Well, thanks, Tinka. It was my pleasure. I just wish we could have been at the Mountain Theater, but maybe next time.
Yes, we all had that same feeling.
Yeah, of course, it's not that nice out right now, so maybe it's good that we were on Zoom. Okay.
Okay. I guess I would like to end tonight by giving three thank yous. I think first thank you is to the Zoom audience for being a part of tonight. I'm sorry, I think there was a glitch with the Zoom link. I hope people were able to join later, but if not, the event would be recorded, so I'll post it on the website as soon as possible. So thank you all, all like-minded, curious audience joining together here. And the second thank you I'd like to give Tinka Ross, the founder of MTAP, who is making these events possible. But most of all, our third thank you to our speaker, Dr. Lynn Cominsky. Thank you so much. I think this was a really engaging and very interesting presentation. I think you covered everything about like gravitational waves, right from I guess like 1970s to all the way to 2024. And good, congrats and good luck to your team for more success and more research moving forward. How about an American Sign Language of silent round of applause? Thank you all.
Okay, thank you. Bye-bye now.